In this video, we are going to start the first method of the three methods that we will cover for calculating the heat of reaction. The first method is called Hess law. This is a method that we use to calculate the heat of reaction with the knowledge of other heats of reactions. This is different from what we did last time. In the previous video, we were using the same reaction. We know the heat of the same reaction, and we did something different. We multiplied by a factor, we changed the phase of one of the components, but it's still the same reaction. In this case, it's a different case because we are using heats of different reactions, other reactions than the reaction that we are interested in. So Hess law states that if we can obtain the stoichiometric equation of reaction number one by doing algebraic operations like addition, subtraction, multiplications by constant or whatever on stoichiometric equations of other reactions 2, 3, and 4, then what we do to the reaction can be done to the heats of reaction. So just to make this simpler, Hess law or the Hess law treats the chemical equations, the reactions, as algebraic equations. So this is how Hess law is looking at the chemical equation. So as we can deal with algebraic equations, we can add them, we can subtract them, we can multiply them by factors. We can do the same thing to chemical equations. And as we can, or what we are going to do to the equations are going to be, we are going to do the same to the heats of reactions. So to make it easier for us to understand, let's take this example, and we will go back after this example to the definition because it will be much clearer. So in this example, we have two reactions that we know that the carbon combustion or reaction of carbon with oxygen to produce carbon dioxide, it has this heat of reaction of negative 393.51 kilojoules. And for the reaction of carbon monoxide with oxygen to produce carbon dioxide, this produces heat of reaction of negative 282.99 kilojoules. So these are the two reactions that we know, and we know their heats of reactions. And we are interested in finding the heat of this should be number 3 of this reaction, which is carbon plus half oxygen to produce carbon dioxide. We don't know this heat of reaction. Of course, these are standard heats of reaction because it has this sub node here. I mean, it's the subscript of the superscript of node. I'm sorry. So this is what we want to do. So if we look at these two equations, of course, none of them is the same equation, but it seems that there is some way we can get this equation from these two equations. By this, I mean that we can do some algebraic operations to these two equations. From these algebraic equations, we can reach this form. So you can look at these equations as algebraic equations, and this arrow as an equal sign. And this is x, y equals z, plus y equals z, for example. So if you have this way of looking at the equations, you can easily tell that this equation can be obtained by getting or by having equation 1 minus equation 2. So if you do 1 minus 2, this is what seems in the first look at the equations. So if we do this, we can do this mathematical operation to check. So if we get the result of subtracting reaction 1 minus reaction 2, then it's going to be C plus O2 minus CO minus half O2. So or minus this whole bracket. So I'm having this side, or this left-hand side, minus this left-hand side, equals this right-hand side minus this right-hand side. So it's exactly like any chemical or algebraic equation. And now you see that the carbon dioxide will cancel, and we have here oxygen and half oxygen. Of course, there is one thing in the chemical reactions that's not possible. You cannot have a chemical reaction that goes to 0. So I can't have a lot of things here go to 0 on the other side. This is not possible. So what we will do is we will take the negative terms here and move them to the other side with a positive sign. Exactly like what we do with algebraic equation. So the oxygen with half oxygen will result in just half oxygen, and this carbon monoxide would go to the other side. So the final equation is carbon plus half oxygen go to carbon monoxide, which is the same equation as this. So by this we are getting what we want. Now this is not the goal. The goal is to find the heat of or the standard heat of reaction. So the standard heat of reaction can be obtained by applying the same operation to the heats of reaction. So I did reaction 1 minus reaction 2, so I will get this heat of reaction as heat of reaction 1 minus heat of reaction 2. So this is going to be negative 303.51 minus negative 282.99 and this will result in negative 110.52. So this is simply Hess law. This is just Hess law. It's nothing more than that. So if we go back to the definition, so it says that if the stoichiometric equation of reaction 1, which is the final reaction that we got at the end, can be obtained by algebraic operations like multiplication by constant, addition, or subtraction on stoichiometric equations of reactions 2 and 3, then the heat of reaction delta HR1 can be obtained by performing the same operations on the heat of reactions delta HR1 and delta HR2. So this is simply what we did here. Okay, so Hess law is very simple, straightforward. It's just addition and subtraction. We don't do anything fancy here. Let's take another example where we have 3 reactions: the combustion of ethane, combustion of carbon, combustion of hydrogen. We know the 3 heats of reactions, and we want to get the or find the heat of reaction of carbon plus hydrogen to produce ethane. There is one thing that must be clear here, that we must make sure that the equations are stoichiometric. So the balance of the equations must be checked to make sure that the equations are balanced equations before we proceed with doing the operations. So now we can see here that we have carbon, we have hydrogen, we have ethane, which are these 3 components. They are already here. So what we want to do now is to find the mathematical operations that we can do to these 3 equations in order to reach this final form. The very simple look at the equations will tell me that this equation must be multiplied by 2 because I have 2 carbon dioxide here. So this must have the same number of carbon dioxide because we don't have any other carbon dioxide. So this is the only carbon dioxide other than this. So we have to multiply this equation by 2. And also I need 2 carbons here, so it agrees with both, that this will cancel this, so this has to be 2 and this has to be 2 as well. Also for hydrogen, we have here 3 hydrogen and we have 3 water, so this must be multiplied by 3 to cancel this. We also know that these 2 equations will have the same sign because carbon and hydrogen are on the same side, and C2H6 equation will be on the other side, so it will have another sign. So either these 2 are negative or this is negative. This is something that is very intuitive. So to decide which one would be the negative equation and which are the positive, we just look at where the compounds or the elements should be in the final equation. So carbon and hydrogen should be on the same place on the left hand side of the equation. So they must be positive. C2H6 is on the other side, so this has to be minus. So the very simple logical interpretation to the equations, or to the idea that we have, that to get the final equation we have to have double the first equation plus 3 times the second equation minus the first equation. This is just by looking at carbon, hydrogen, C2H6. We haven't checked if oxygen will be cancelled out at the end. We haven't checked if, and it's mainly oxygen. The rest are kind of checked. So what we will do now is we'll write the equations and we will check and see if we will reach the final form or there is something wrong. So this is what we have. Double the first equation, so it's 2 multiplied by carbon plus oxygen. This is 2 multiplied by the first equation plus 3 multiplied by the second equation, so 3 multiplied by hydrogen plus half oxygen minus the first reaction, so these are going to be on the other side, so it's plus 2 carbon dioxide plus 3 water. Then the result is going to be 2 carbon dioxide, 3 water, and the C2H6 plus 7 over 2 oxygen. So now let's simplify the equation. We have here 2 oxygen, we have here 3 over 2, so this is 3.5. We have here 7 over 2, which is 3.5, so these will cancel. And we have also here 4 carbon dioxide, 2 carbon dioxides here, 2 carbon dioxides there, 3 water, so we will end up with 2 carbon, 3 hydrogen, and 1 C2H6. So this is the final shape of the equation that we will have at the end. And as we said, this is not my goal. My goal is this, the heat of reaction. So we will do calculate the heat of reaction as double the second reaction. So it's 2 multiplied by negative 393.5 plus 3 times the third, which is 3 multiplied by negative 285.8, minus the first reaction minus the heat of the first reaction, negative 1559.8, and this will be equal to negative 84.6 kilojoules. So this is simply Hess law. There is nothing more than this. It's very simple, very nice way of calculating the heat of reaction. So next time we will be talking about the second method. And by the way, the second method and the third methods are both an indirect application of Hess law. And this is something we will check next time and the next 2 times. This is something we can get by just simply applying Hess law in an indirect way, which is using the heats of formations and the heats of combustions. So we will see you next time, inshallah. Goodbye.